We're going to start with our first speaker, an invited talk by Michele Piana of the University of Genova in Italy. The talk's title is Artificial Intelligence for Space Weather Forecasting, Data-Driven and Physics-Informed Approaches in Research and Operational Settings. Michele, you have 30 minutes for your talk. I'm going to give you a warning at 10 minutes before and then 5 minutes. And then we're going to have 10 minutes of questions and discussions. We are all ears. Go ahead, Michele. Thank you.
Okay, thank you. Thank you, Manolis. Can you hear me?
We can hear you fine, yes.
Okay, good. So first of all, let me thank you for the invitation. Let me thank Carmen for all the effort. I'm very sorry for not being able to be there, but these times the teaching duties are very, very strict. In any case, so what I try to say today is some reflections about our viewpoint on some issues that are troubling us in the group in Genova, and I would like to share these reflections with you. So the idea is to describe 4 issues that, according to us, are a little bit crucial for understanding the use of machine and deep learning for space weather forecasting, and also for trying to make these approaches effective in operational settings. So the first issue is related to how to define a validation strategy, a shared validation strategy for these algorithms. And this is has something to do with both the way we generate training and validation and test set in the case of supervised approaches, and on the way we provide the results, the skill scores that assess the effectiveness of our predictions. This is somehow related to the fact that we need to account for the cyclicity of solar activity in the generation of these sets, and so these 2 first issues are in some way intertwined. Then we think that it is important to understand some aspects related to the computational burden of the training of the algorithms, and this is related mainly probably for nowcasting and for operational purposes. And finally, I would like to share some reflections about how to use physics in order to improve the prediction performances of the methods. So let's start with validation. And as I said, I think that there are 2 issues we should consider. The first one is how to generate training, validation, and test sets in a way which is in some form standardized for all the approaches. So we know that chronological splitting is probably not the best way to generate training, validation, test set, and this is related to the cyclicity of the solar activity. And also we know that even from a foundational viewpoint, we need to use more or less the same probability distribution to generate training, validation, and test sets if you want that machine learning is in some sense compliant with the theoretical requirements. So this is the first issue. The second issue is that we need to provide results with some error bar, with some uncertainty. This is obvious, and so probably one way to do this is to use bootstrap analysis, but also in this case we have to pay attention to the fact that, for example, in the case of flare forecasting, if we decide to generate a bootstrap analysis, and to do this we want to generate many realizations of a training set made of active region images, we have to pay attention to the fact that we need to keep active region separation in this generation procedure. Okay, so to trying to be compliant to these requirements, so this is what we think. So we need to provide a clear-cut definition of data samples. For example, in the case of flare forecasting, so it is rather easy to define the data samples related, for example, to a specific class, flare class. This is an example using videos. So a input data, which is an X-class video, is a data sample made like this. You have a video, for example, a 24-hour video of HMI frames, and then you annotate it, you compute the label, looking if in the following 24 hours there is the occurrence of a flare or of an X flare. The same for the data sample related to an M-class video, and the same is for the data sample related to a C-class video. But things are a little bit more tricky if you want to define data samples related to null events. Of course, it's easy to construct a data sample related to a video made of HMI flares and labeled in such a way that there is no flare at all generated by that specific active region. But you have, and this is no one, so the no one class. But then you have three other classes that may occur. For example, you may have the no class 2, where you have a video, a 24-hour video as input sample for the network. You have no flare in the following 24 hours, but after that, you have flares in the following 24 hours. Or you may have this different situation, so in no class video 3, where you have you record the input video during the emission of during the occurrence of the flare, and you have no flare in the following 24 hours. Or you are in a situation like this: you have a video where nothing happens, but something happened before that video. So these different classes should be accounted for when you generate the training, test, and validation sets, because if you do not do that, the results, as I will show soon, can be extremely different. Of course, at the same time, the idea is that you need to generate training, validation, and test sets that account for these classes, and this can be done by accounting for the rates with which these kinds of data samples occur in the set. Of course, as I said before, you need parsimony, so you need that each subset of samples is made as few active regions as possible, and this means that samples that belong to the same active region must belong to the same data set. Okay, so we try to account for these aspects in an experiment we made using SDO HMI images that have been recorded in this time frame, and we generated the 24-hour-long time series of HMI frames, and everything, as in the previous example, was labeled, setting 1 if a flare occurred in the following 24 hours, or 0 if nothing happened. And then we generated many realizations of the training, validation, test set to perform bootstrap analysis. This is the architecture we used. It's a convolutional neural network coupled with a long short-term memory network for the classification. And in both cases, we used probabilistic loss functions for the training that are able to a priori optimize some specific skill score. In this case, we used TSS, but results are rather similar for other skill scores. okay, these are some examples. So, for example, suppose that you want to perform the prediction of flares of C-class and more and higher. Okay, if you use an entire test set that has been generated accounting for the rate of X-class flare, M-class flare, C-class flare, and the 4 different definitions of samples for the null case, and you use all the test set. This is the skill score we obtained using TSS. But if you throw away from the test set this case, so no class 3, when you have the flare during the recording of the input video, but nothing in the following 24 hours, you have an increase of the score, and this increase is maintained if you throw away no class video number 4, which are made of videos that have been recording while nothing happened, but you had flares before the recording. And this is also true if you exclude also null class video number 2, which are the videos that have been recording in such a way that nothing happened in the following 24 hours, but you have C flares after that. So as you can see, it is important to agree about how to generate these null events in the training set, validation test, and test set if you want to compare results. And this is true also for the prediction of M plus flare. For example, this is the score we obtained keeping all the null events in the set. If you exclude number 3, number 4, and number 2, the scores are more or less the same. But if you exclude C-class videos, all of a sudden the TSS value increases, and this is absolutely reasonable because C-class flare may confound the network with respect to M-class flare, much more than null events. Okay, this issue of generating training validation test sets has a lot to do also with the cyclicity of the solar activity. For example, if you want to predict flares in this time window where you have an increase of the solar cycle, it is much more reliable if your training is made using data that have been collected in some historical archive in the time window that corresponds to the same phase of the solar cycle. Because the results may be significantly different if you do not account for this aspect. We made this experiment. So the test window is March-December 2015. We used essentially the same data, HMI videos we considered in the previous example. This March-December window is in the decreasing phase of the solar activity. And here you have the comparison of the TSS. If you train your network in the same, using data in the same phase, or in a phase which is completely different. In this case, we consider a phase where there is a plateau, so we are at the maximum of the activity and not in the decreasing phase. This is true for prediction of C plus flare, but this is also true for the prediction, even more true, for the prediction of M plus flare, so where the difference between the two scores is even higher. Okay, so this means that we need to agree about how to generate training validation test set if we want to compare our algorithms and the performances of our algorithms. At least this is our opinion. And the other thing is we need to account for some computational issues related to the fact that at some point we would like to have our algorithm ready for operational settings. And to do this, we need to understand, I think, that probably using feature-based machine learning could be more effective than using deep learning for images or videos. And this is because if we need online training, we need to go faster, and training feature-based machine learning is in general at the moment faster than training deep learning CNNs. And this is even more important because what we realized is that if you consider feature-based machine learning, at the end of the story, the number of features that really matter, that have a significant impact on the prediction performances, are rather few. So let me show this experiment, again related to flare forecasting. We used a little bit larger time window of sharp images, and we extracted a lot of features from these images using the routines we developed during the FlareCast project that Manolis led some years ago. So 171 features have been extracted using these routines. So it's, I think, a very notable amount of data. And we created more than 4,000 sets of vectors with dimension 171. What we realized is that, as I said, the features that really impact the prediction performances of the algorithms are more or less always the same. So, for example, here you see what happens in the prediction of at least C1 flares and at least M1 flares using two different algorithms. These are feature-based algorithms. One is a hybrid lasso, the other one is a random forest. And as you can see, if you make a feature selection, a feature ranking process to the feature you used during the training of the algorithms, and you look at the top 10 ranking features, you see that you obtain more or less always the same features, independently on the kind of prediction you want to make, and independently on the regularization network you used for the prediction. And here you have the example of two algorithms, but during FlareCast we developed a lot of algorithms, and more or less the result is the same, whatever feature-based algorithm you use. This is true also if you change the issuing time in the training set, more or less always the same features in the first 10 ranking features in the game. And what is even more interesting is that the number of features you need to make a reasonable, reliable prediction is even smaller than 10. This is what happens if you make the prediction adding one feature at a time. So the dashed line corresponds to the optimal prediction used by the two different algorithms, so hybrid lasso and random forest. And as you can see, in more or less all issuing times you consider, you have that after 4, 5, 6, maximum 7 features, you reach the plateau, you reach the asymptotic behavior. So I think that this tells you two things. One is that probably we have a very redundant amount of information in our hands, and probably this may be the origin of some limitation on the prediction performances of the methods. But on the other way, we think that this is a nice piece of news if we want to make operational forecasting. So if we want to make online training, because we do not need to train so many features during this online process. Okay, so this was what I would like to say about these aspects related, a kind of common feeling on the use of these algorithms for flare forecasting. But then I would like to tell you something about what we are doing in Genova in the case of the use of physics in order to increase the performances of our machine learning.
Michele, you have 10 minutes.
Yes, yes, thanks. Yes, but I'll do that. Okay. So this is a tricky problem, and we are not absolutely sure that if we are doing the right things. So in general, but again, please tell me if I'm wrong, we may consider two different approaches if we wanted to plug some physics inside the machine learning game. One is starting from deterministic equations, so physics equation, in general, magneto-hydrodynamics equations. These equations have parameters that must be constrained somehow, and we may use machine learning or deep learning in order to help support the optimization of these parameters. But on the other way around, we may have a second approach where we start from the machine learning algorithm and we try to use physical models, deterministic models, in order to improve the performances of the algorithm. And this can be done, probably, at least one way that this can be done is to encode the information coming from physics, coming from the model in the training phase, which means in the loss function used for the training. This may have some problem because these models have parameters inside, and you need to optimize these parameters, and this can be done using physics or, again, using machine learning. Okay, I would like to show you some preliminary results that are concerned with the prediction of the travel time of coronal mass ejections. The input data are parameters measured by remote sensing instruments like LASCO, or now we will have METIS in solar orbiter. And you also need some measurements obtained by in situ instruments, like, for example, CHELIAS or now SVA. And we used the very easy drug-based model in the training phase. And what we want to predict is the time of arrival of the theory. Because these are the input parameters we used for the networks. So you see there are some the usual parameters used for CMEs and a couple of parameters related to the solar wind. But of course, you also have one parameter, which is the drag parameter, which is a parameter proper of inherent the drag-based model, and this is this parameter C here. So this is the differential equation for the drag-based model. You can integrate exactly, analytically, this equation. But if you do that, you have a non-differentiable result. And we need a differentiable result because we want to plug the solution in the loss function. And if you want to optimize the loss function, you need that it is differentiable. And so this is an approximate solution of the differential equation for the drug-based model. Okay, this is the kind of architecture we used. So it's a cascade of two different neural networks. The first one is a neural network that it is used to predict, to estimate the drug parameter C. And then you have, in cascade, a second neural network that it is used to predict the travel time. The first neural network has a totally physics-driven loss function. So as you can see, this is the plug-in of the drug-based model solution in the loss function. The second neural network, which is the one used to predict the travel time, is a weighted sum of a completely data-driven component, which is an Euclidean component, plus the usual drug-based model-driven loss function. So if you use this cascade, you have 6 possible configurations. One configuration is totally data-driven, so you have no, the first network is switched off, and you have just data, no parameters, no C parameters anyway, and you must use a completely data-driven network in a loss function in the second network. But you may also have the first network switched on, and in this case, you estimate C, and you may or may not use C as an input feature in the second network. These are the results. So these are the mean absolute error for the 6 configuration. And as you can see, the best one is this of C5, where you have both networks on. The drug parameter is used as a feature for the second network, and the loss function for the second network is the perfect balance of the two components. In general, what we have is that if you use C as a feature, you have better result. This is also true in the fact that you have less outliers, a smaller number of outliers. And if you look at the best performances over the 100 possible realization of the test, training, and validation sets, you may, if you use C, if you use a physics-informed configuration, you have a very small best mean absolute error, and you can even go down at values lower than 5 hours. And this is confirmed by the fact if you make some feature ranking, you obtain that the drug parameter has a very high rank essentially in all realizations. So work in progress. We need to do more experiments, and we need to plug in good skill scores in order to determine the quality of our performances. And for example, we think that we need to consider skill scores that are more related to the value of the prediction more than the quality. This is an example. So if you look at these two synthetic cases of prediction, the predictions are in red, the actual occurrences are in blue. You can see that these two configurations have the same TSS, but these are completely different configurations. The first one makes a lot of false positive alarms, while the second one makes some false positive alarms, but they are closer to the occurrences of the prediction. So we think that we need to account for these aspects when we want to assess the performances of our algorithms. So these are some references. We are hiring people, so if you are interested in coming to Genova, Genova is a nice city, to work with us at these things, please send an email or look our webpage, and thank you for everything.
Thank you, Michele. That was very, very interesting, and thank you also for keeping in time. We have 10 minutes for questions and discussion in general. So let me ask the physical audience first about any questions or comments.
Good talk, thank you. I wanted to ask about the part where you mentioned CME arrival time prediction.
Yep.
And what I saw in those parameters were the projected parameters from LASCO, or I think mainly from LASCO.
Yes.
So have you tried them with corrected parameters or true parameters, removing the projection effects? And if you do you see difference in the prediction of the arrival time?
That's a good question. These are preliminary data, but yes, we accounted for projections, and we obtained a slight improvement of the predictions.
Right. So so when you take into account the projection effects, does the ranking in the features, when you try to find true skill score, does it change? Right.
Yes,
which parameters is more?
It's very difficult. Send me an email. I have to ask the young guy. I didn't. Okay, I've not this detail, but send me an email and I'll let you know. Yes.
Right. Thank you. Thanks.
Okay, you're welcome.
Question right on your back.
Hi, Michele. Shane here. Thanks
Ciao,
for
Shane.
talk. I was just wondering, in the first part of your talk where you mentioned about excluding the null clauses or the null cases, could that be interpreted as the model over-predicting flares? Essentially, when you remove more and more null cases, your skill score goes up. So you're always predicting a flare, but it doesn't always happen, essentially.
That's the point. Absolutely, Shane. So what we realized, if you want the warning, again, I'm not sure. I don't want to give warning to people, but what we consider is the fact that if your training set is not well balanced, also in the case of null events, things may change significantly. And yes, you can over-predict the flares. That's the point.
Okay.
So we think that we need to generate a training, validation, and test set that have the same rates also in the case of these different kinds of null events.
Thanks.
Okay.
Any more questions or comments from the physical audience before we get to the virtual audience?
Hello. I would like to ask about the loss function, the second neural network that you used.
Yes.
How did you choose to make the balance as with
that's
the
a very
lambda?
good point. Very good question.
Yeah.
Okay. Very frankly, we are doing this heuristically. Okay. We changed we sampled many different values of lambda and look at what happened. And things are not exactly the same. Okay. You don't obtain exactly the same performances. And what we are showing here is something related to easy, very simple-minded choices. So lambda equal to 0, lambda equal to 0.5, lambda equal to 1. What we are trying to do from a completely formal viewpoint, mathematical viewpoint, is to use this lambda as a regularization parameter, because in some sense it is a regularization parameter, and to try to find an algorithm that provides you with the optimal value of lambda.
Okay, thank you.
You're welcome.
More questions or comments? One behind you.
Yes, thank you very much first of all for the interesting talk. My question would be about the comparison of your classical machine learning random forest algorithm to neural network. So first outtake which I got, so in principle random forest works even better, right, when you're working with this manual feature extraction scheme. my question would be, which kind of optimizer did you use during the training, and how I guess it probably used L2 regularization scheme, I guess, not L1. How
No, we used L1.
You used
L1.
L1. Okay,
yes.
So because I mean, my second question would be about the outliers. Would it be really robust to outliers?
Oh yes, both random forests and hybrid lasso. So yes, they have very similar behaviors. And yes, we used L1 first. Second, I think that we used the Adam optimizer for the optimization. And third, there is robustness. Yes, there is robustness.
Thank you very much. Great.
Yes, you're welcome.
Okay, we have one question online. So please go ahead.
I'm assuming it's probably me. Can you guys hear me okay?
Yes.
Yes, we can.
Okay, I have two questions. I'm going to choose one, and then if there is time, I'll ask the second one. But you mentioned the importance of accounting for the solar cycle in all these methods. And the solar cycle is 11 years or 22 years, depending on how you want to account for that. But I was also thinking on the timescales for a solar flare, that is just a couple of hours. And if we see the examples that you provide in your slides, you are training basically with videos of 24 hours or so. And then in the end, you show how what you are trying to model is the CME propagating across the heliosphere, basically. So, which is another timescale. And the question is, I want to get your thoughts on the importance of different timescales when you are trying to forecast solar flares, either data-driven or physics-informed, all of that, but like how the time plays in all of this.
I think your question is very good. Okay, so the examples I showed about the generation of sets in the accounting for solar cycle is related to flares, while in the case of the CMEs, we try to account for that, but we didn't do that so far. But you are totally right. We need to agree about what to do considering the different scales of the space weather phenomenons. So it's completely different, and this is another issue we should consider. So the time scale of what happens, and probably this should be done also in the case of the prediction just of flares, just of CMEs. So in the generation of the training set, we should consider the fact that these events are characterized by different time scales. We need to do that. I agree with you.
Thanks.
Any more questions? You mentioned you had the second one, so could you please?
Yes, can I do it?
Yeah, sure.
So yeah, no, the other question is about HMI itself. So you mentioned also that you use the SHARP data from HMI.
Yes.
SHARP is basically cutting the active regions. And with that is one is you are not considering what is happening everywhere else on the solar disk that may become problematic. And the big question there is, even during a solar flare, it's very questionable how HMI data changes and the kind of features that you can see even during the maximum of a flare. I know we use GOES X-ray flux to as the pattern to train the models. But the question is whether we should keep using HMI data by alone, isolated, to train all these models, or if we need more data aside from HMI.
Yeah, so Yes, I agree again with your questions. So let me say a couple of things. First, yes, you are right. If you use feature-based methods using sharp data, there is the risk that the way you cut the images is not the optimal one, and this is a point scored by CNN, because if you use the full disk images as your input data, that you don't have this problem. Second, we use ghost data to label, to annotate the sharp data. And third, yes, we need to, absolutely yes, we need to go to a multimodal approach. We are doing this using both HMI and AIA data at the moment. Very preliminary stuff. But yes, I think we need to use different modalities.
Thank you, Michele.
You're welcome.
Any more questions? Here's a quick question, Michele, from me.
Yes, yes, Manon.
Do you think that we can use physics-informed machine learning as solvers of differential equations, equations with partial derivatives? I happened to hear an opinion some time ago that you can do that, but with an accuracy that is no match for the analytical or the semi-analytical methods. So it's pretty much a wasted time to try to use physics-informed neural networks for solvers. Is this your opinion, or you have a different opinion?
Okay, I agree with you. I think that when I wrote these two possibilities, because these are the two that we are trying to understand at the moment in Genova.
Okay.
So we are not working at the use of machine learning to solve the MHD equations, but that just to constrain some parameters in the MHD equations. I think that it is true that probably the analytical solutions are better, but it is also true that when you compute the analytical solution, you make some assumptions, and you are not completely sure that these assumptions are true. Sure. And so machine learning approaches give you more generality in the solution. So it's a tricky thing.
So it's a trade-in we have to be aware of.
Yes,
much
yes,
better than
so.
we are now. Okay.
Yes. Okay.
Thank you very much, Michele.
You're
Let's
welcome,
thank
Manoj.
again, Michele.
Thank you. Thank you. Thank you.
For the very interesting presentation.